Right, let's do about 4 or 5 problems, and what we're going to do is we're going to look at what it means to be a solution to a differential equation. So let's come over here and let's go super old school. And let's say I had the equation x plus 4 equals to 10. Now, in our heads, I know we can all do that the solution to this is x equals to 6. Well, what does it mean to be a solution to this equation? Well, it means that we found the x value that makes this a true statement, right? 6 plus 4 equals to 10. This is actually the unique solution. This is the only solution to this equation. So come back over here. These are all differential equations. Well, what does it mean to be a differential equation? Well, it means it's an equation that's relating the derivative to x and y. This one is y prime is equal to 4y. This one is p prime is equal to 2 times p minus 10. So the y prime is related to y, p prime is related to p. This one over here, this is y prime is related to x and y. This is y double prime is related to y. All of these are in the category of a differential equations. These three happen to be separable differential equations, and we're going to look at this one as well in terms of what does it mean to be a solution. So let's look at this first one, and let's say we do some math, and again, you can look at a different video on how to solve a separable differential equation, but what I'm going to look at is what does it mean to be the solution, okay? So I'm going to claim that the solution to this particular differential equation is y equals 10 e to the 4t. And again, so we already decided, what does it mean to be a solution? It means that you are finding the y value that makes this true. It's just like finding the x value, x equals 6, that makes this a true statement. Except instead of finding an x value, I'm finding the function. I'm finding the function that makes it so that the derivative of the function equals 4 times the function. And I'm claiming that this is the solution. And what I'm going to look at is I'm going to check it. Okay? So again, if I'm claiming that this is the solution, I can just plug it into this and make sure I get a true statement. So if this is my function, what is dy dt if this is my function? Well, what's the derivative of this? The derivative of an exponential is 10 e to the 4t times 4 using the chain rule. And what I'm claiming is that the derivative equals 4 times the function. Well, the function is right here, 10 e to the 4t. And of course we look at this and we say 10 times e to the 4t times 4 is the same thing as this. So I've verified that this is indeed the solution to this. And maybe you've already watched a video on exponential growth and decay, because if you translate this into English, this says the rate of change of the population is proportional to the population itself. And so it's not a surprise that an exponential growth function describes this same behavior. Again, this is saying that the function is exponential, and this is saying the exact same information. dy dt, the rate of change of y is proportional, meaning some number here, to the population itself, right? This is percentage growth, and that's what exponential. And again, I'm just proving that this is actually a solution. Okay, let's come down here. I claim that p is equal to 10 plus 4 e to the 2t. Again, that's one of the solutions, but I'm going to claim it's a solution to this. Okay, what I'm claiming is that this function satisfies this. So let's plug back in. What is dp dt? Well, if you take dp dt, the 10 goes away because the derivative of 10 is 0, and then the derivative here will just be 4 e to the 2t times 2 using the chain rule. And I'm claiming that's equal to 2 times p, well there's p, 10 plus 4 e to the 2t minus 10. I'm claiming that this is a true statement. The 10 and the 10 cancel. 2 times this is the same thing as this. Boom. This function satisfies this differential equation. Okay, what about this one over here? This is actually a non-separable differential equation, but let's claim that we knew, or at least we think, y equals sine of 3t. That I'm claiming that this function satisfies this. So if you take two derivatives here, take two derivatives of a sine function. The first derivative, well, let's show our work. The first derivative, you're going to get 3 cosine of 3t. And then the second derivative is going to be a negative 9 sine of 3t. And let's plug it into this and show that it works. So this is claiming that the second derivative, well, here's the second derivative, negative 9 sine of 3t equals negative 9 times our function. And our function is right here, sine of 3t. And look, equals. Meaning if this is equal to this is a true statement, which means this is indeed a solution. I'm not guaranteeing it's the only solution. Someone might be saying, well, how'd you know it was sine? Maybe it was cosine. And go ahead and do that exercise on your own and prove that cosine of 3t also would have worked for this. They both would have worked. And again, you can think about, well, what about in this case? You know, would it have to be a 10 there? And it turns out that the 10 didn't matter. It could have been a 5 here, and this still would have satisfied. So I'm not guaranteeing I found the only solution, but I am guaranteeing that this is a solution to that. This is a solution for that. And this sine of t and actually cosine of 3t is a solution to this differential equation. And we know this is true. This happens all the time in math. We can say x squared minus 4 equals to 0. That has two solutions. X can equal 2 and x can equal negative 2. So there certainly are lots of times when we have just regular equations where we have two solutions. Well, here's an example where you have two different solutions for this. You can even say that this is the solution. Y equals 10 cosine of 3t. And you can show that this is also a solution to this differential equation. Okay? Again, we're finding not the solution, we're proving that this is a possible solution. Okay, how about this one down here? Let's claim that y equals e to the x squared minus 4. We're going to claim that this is a solution to this. So take the derivative and get 2x e to the x squared minus 4. And is that equal 2x times y, which is right here, e to the x squared minus 4. Okay, and you see that this equals to this, which means this is indeed a solution to this differential equation. Okay, so all of these didn't have initial values. Now, if you take any one of these functions and give it an initial value, then you're going to guarantee that you can find exactly that has to be 10, that this has to be 4. And again, that's looking at a different part of a differential equation, but again, just verifying that something is a solution, all we're claiming is that this satisfies this. Okay, so how does this kind of go to the next level? Well, here's the next level. So let's take this as a differential equation, and what I'm claiming is that I can find a line. Any line can be written in the form y equals mx plus b, and I want to find the line that satisfies this, even though this is a non-separable differential equation. Again, normally how you'd find the solution is that you would solve a separable differential equation. Let me show you that real quick. So let's go back to an example on the front. Let's say that dy dt equals to 4y like we had on the front. And let's say that we know that y of 0 equals 10 or something, right? This is some initial value. So how do we solve a separable differential equation? Well, we separate the variables. dy over y equals 4 dt. Once they're separated, I can integrate. The integral of dy over y is the natural log of y. The integral of 4 dt is just 4t plus c. And now I'm going to use this initial value, and I know that when t equals 0, y equals to 10. So the natural log of 10 equals 4 times 0 plus c. So now I know that c is just the natural log of 10. I come back here and I say the natural log of y, and again we can drop the absolute value, we're only dealing with positives here. 4t plus the natural log of 10, right? I know what c is. C is the natural log of 10. I just put that in, and then I'm going to exponentiate. What that means is that if these two things are equal, then e to those powers also have to be equal. E to the natural log of y is just y. E to the 4t plus the natural log is the same thing as this. Again, remember your exponent rules. E to the 4t plus the natural log of 10 is the same thing as e to the 4t times e to the natural log of 10. But e to the natural log of 10 is just 10, and I get 10 e to the 4t. Again, this is just 10. So what I did here is I took this differential equation and this initial value, and I solved a separable differential equation. I separated, integrated, found c, and then found y. Finding y is just using some algebra. And again, I found the particular solution to this differential equation. And again, on the front, I proved that this is a solution to this. Okay, this is a non-separable differential equation, but the AP can still ask you to find m and b. These are unknowns, but you can find m and b that make this a true statement, meaning they'll say something like, find m and b that make this a general solution to this differential equation. Okay, so let's just do what we did on the front. It's really not that hard. So we're claiming that this needs to be true for this function. Okay, so what is dy dx if I claim this is the solution? Well, what is dy dx of this line? Well, the slope is just m. So dy dx has to be m. And we're claiming that m, meaning the derivative of this, equals 2 times y, but I'm claiming y is this, mx plus b plus 4x. Okay, this has to be true for all x, not just for one x. This can be x equals 0, x can equal 5, x can be whatever I want to be. So very similar to partial fractions, what would happen if x was 0? If x was 0, this still has to be true. So if x is 0, I claim that m equals, if x is 0, this is just 2b. This is 0, this is 0, so m equals 2b if x is 0. All right, so I know that has to be true. But what if I want x to equal 1? Still has to be a true statement. And so I get m, okay, let's do nice and slow here. I get m has to equal, if this is a 1, this is m plus b. So this is 2m plus 2b plus 4. Again, I'm just letting x equal 1. And what we're going to do here is, well, if m is equal to 2b, I can just put a 2b in here everywhere. So this is just 2b. This would be 4b plus 2b plus 4. Those cancel, and I get 0 equals 4b plus 4, and I get b must be negative 1. But if b is negative 1, m is negative 2, and voila, I know now that this particular line, negative 2x minus 1, is a solution to this differential equation. You can check it if you want to. Just do what we did on the front. Take the derivative and get negative 2. All right, we're claiming that negative 2 has to equal 2 times y, there's y, negative 2x minus 1 plus 4x. And look, negative 2, negative 4x, but 4x, negative 2. Negative 2 equals negative 2, meaning this is indeed the solution. And again, the AP likes this question on a BC test because it gave you a differential equation. The one isn't separable, but they gave you some sort of solution idea and said, you know what, I think this line is the solution. See if you can find m and b that make it satisfy this equation. So just do this equation. Set dy dx equal to 2 times y plus 4x, and then this has to be true for all x. So I just picked easy ones. Pick x equals 0, pick x equals 1. It gives you 2 different equations, 2 variables, solve. And again, we solve a system to find negative 1 and negative 2 are the solutions. Again, a solution to a differential equation is the function. Again, all of these, if I said solve this equation, you'd get this. Solve this, you'd get this. And again, you'd have to have some initial values to get the particular conditions here. But again, this video was all about proving something is a solution to a differential equation, which you could always do at the end of a problem to make sure you did it right. Hopefully it helps. And again, there are going to be some harder videos to look at in terms of solving more difficult differential equations. But this is all about verifying whether something is a solution or not.